Want to hear our word stories?
Yes, after class. Hello and welcome back to Differential Equations, section 5.1 and 5.2. They tie together into this one story on linear systems. We are going to focus on the first order, peek into the second order a little bit. We're going to cover the method of elimination. So you know now you have a linear function with x and y as variable, and then you add another linear equation, and you have a system of two linear equations, and you find the intersection point to get you x comma y, which is the solution to that linear system. Now we are going to have a system of differential equations. The book starts from the point where they describe certain application, whether it's mixing of two, so you have two tanks that are connected with two tubes, and then the water and whatever other solvent are going to those tubes and they're mixing. You can also look into the systems with a spring and a mass, where you have two springs and two masses. They all attached and they dangle in space. So one will obviously affect the other. We have circuits with two loops. We use Kirchhoff's laws to create differential equations going around. By far, those are my favorite, obviously. And you get system of two differential equations. And then you use these methods to solve those. So there are plenty of applications for these linear systems. So the chapter 5 is focusing on dealing with the problems that have these linear systems. Now, what is a linear system? So we are going to have, so linear system will contain at least two functions. So one function which is independent variable x, x prime, x double prime, dot, 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 equal to 0. And then another function of maybe I should couple them. Okay, let's do the x, y, x prime, y prime, dot, 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 maybe better. And then again, different type of the same with a different function, different configuration. So these are those explicit forms that take everything into account. I'm just going to give you a very quick example. We're not solving this, it's just example to see what they look like. So let's say you have x prime is equal to knowing 3x minus 2y, and then y prime is equal to x plus 5y, whatever. So this is a linear system of two first-order linear differential equations, and we are going to learn how to solve this in this chapter. Again, applications are many, so you come up with, you have the application, then your application would spell out these type of equations, and then we learn how to solve them. Now, before we do that, there are methods of converting, let's say, third degree or the second degree equation into these systems. And also there are methods that would combine systems into second order, third order differential equation. So in some cases, one way of solving is easier than the other. So we learn both ways of going forward and going back. In 5.1, you do not learn methods of solving. You learn how to convert one system into another. And then we start with 5.2, method of elimination. And then we go into matrices, and then eventually even eigenvalues and eigen stuff, right? So to start off, let me pick an example for the second order linear differential equation and then break it into two equations. So I'm just going to jump into homework and pick one of the examples, and then if I hit one of your homework problems, just move away from it, one up or one down. So equations, problems 1 through 10 are the problems that are converting this. So let's take a look at maybe problems 1 and 2, and then you deal with problems 3 to 10. Sounds good? So to explain the concept using the easiest, and then you also have the examples given in the textbook. So you'll have at least 4 examples worked out. So x double prime plus 3x prime plus z ben x is t squared. And we want to convert this to the first order system. All right. So to convert this to the first order system, I can use variables or functions, right? x1 and x2, for instance. So x is a function of t. Let me start by spelling that out. I know you all know it, but x is a function of t. You are used to y, but in this case, so you write x of t, right? And then there is some solution, so I'll just say blah over here. There is some solution, and this is the second order equation, so you are going to have, right? You know how to solve this using old methods in chapter 2. Now we're learning something new. So you have this, and what I'm going to do is I'm going to define, right, to break it apart, I'm going to define x1 is equal to x, and x2 is equal to x prime. So these are the two definitions that I make. Now, how do I know that I'm supposed to use two of these? Well, it's a second order equation. So I know that I'm supposed to define two. Now, it's defined in a clever way because you're replacing x with x1, so that's 1 to 1, right? But then you have x prime with x2. So how does this help, right? Well, you can...
Are you going backwards? Like, is that 7x the x1? Does that x belong to that 7x?
Well, we're going to plug the stuff in, yeah. But first I need to differentiate these two puppies. So x1 prime is x prime, and x2 prime is x double prime. Do we all see that? So all I did is I differentiated. So I made a definition up there. You can say define, you can say let, right, whatever. And then you differentiate them. And now we want to come up with what these things are. Now, we need to have x1 prime is equal to something, and x2 prime is equal to something. So this is our goal. Now, we already know that x1 prime is equal to x1, but we are not allowed to use x, right? We are not allowed to use x, but luckily we know that x prime is equal to x2, because let me just write like this, both in terms of x1 and x2. So you're no longer allowed to have single x. You have to have x1s and x2s everywhere when you do this. So we know that x1 prime is equal to x prime, and we know that x prime is equal to x2. So by those two, x1 prime is equal to x2. When you compare, let me actually do the colors here. So this one gives that one. So this one would be what we need, but we are not allowed to have x prime. So you go and you look for x prime in terms of x1 and x2, and we do have it that x prime is equal to x2. So x1 prime is equal to x2. And that gives us the first equation. Now, the second equation, x2 prime is equal to x double prime, right? But now x double prime from the original equation up there is given as t squared minus 3x prime minus 7x. You are not allowed to have x's in this, so you will replace them using, again, your conversion formulas. You will replace all of them with appropriate x1s and x2s. So first equation, x1 prime stays as is, which is x2. And then x2 prime is equal to t squared, stays as is, minus 3. X prime is x2, 3x2. X, so minus 7x1. Because we have that x is equal to x1, right? That's this part. And if you look at my newly obtained system, there are no x at all. It's just x1s and x2s and their derivatives. So this procedure took a second order linear differential equation and broke it into a system of two first order linear systems. Observe that there are no second derivatives anywhere. But these are coupled equations, right? And yes, we can find a solution, right, grinding through this stuff. But these are these equations are in a different form. It represents the same problem, you will get the same solution. It's just in a different form. So now what you have here is the system of two first order linear equation. That's what you have. And we're done. That was the goal. The goal was to transform the second order system into these. Then now I said I'll do the second problem as well, and then you do 3 through 10 for practice. So the next example, the next problem is to transform, and I picked number 2 because it is the fourth order in there. So number 2 has x to the fourth derivative plus 6x squared minus second derivative of x. So x to the I can't speak. Fourth derivative of x plus 6x, the second derivative, minus 3x prime, first derivative, plus x equals to cosine 3t. How many equations? Well, it's the fourth order, so better be 4. Exactly. So we start from the back, right, from with x. So x1 is x. x2 is x prime. x3 is x double prime, and x4 is x triple prime. I can put 3 tick marks in. Yeah, 1, 2, 3. There we go. Not bad. Great. Now remember, the next step is to differentiate each one of these because you need to hit x fourth derivative. So x1 prime is x prime, x2 prime is x double prime, x3 prime is x triple prime, and x to the fourth prime, x4 prime is x to the fourth derivative. And now you know that you have to create the system where x1 prime is equal to whatever you get, but only in terms of x1, x2, x3, x4. You are not allowed to use any single x's. Ever, yeah. And then x2 prime needs to be, again, some blah in terms of x1, x2, x3, x4. x3 prime, same. And x4 prime, same. So these are our what we need. So this is what we need. And now we go and we stare at what we have in these combinations to find the key of how to connect all of these. So x1 prime, I look for x1. x1 prime is x prime, but x prime is x2. Great. Do we all see the way I thought about it? So I need x1 prime. I go and I find where my x1 prime is, which is here. That's where x1 prime. Now x1 prime is equal to x prime. I'm not allowed to use x prime, but there has to be an equation in the first row that tells me what x prime is in terms of x1, 2, 3, 4. And that's this one. So I was able to determine that x1 prime is equal to x2. Then I move to x2 prime and use the same reason. I find where the x2 prime is, and I see that it's equal to x double prime. I'm not allowed to use x double prime. I go to the first row and see what x double prime is equal to, which is x3. So x3. And then I go for x3 prime. Again, x3 prime is right here, which is x triple prime, but that's x4, right? Because it's right there. You just connect them. And then finally we have x4 prime. Now x4 prime is equal to the x to the fourth derivative, but that's given in the original equation. If you solve the original equation, you get cosine 3t minus 6x double prime plus 3x prime and then minus x. We are not allowed to use any of these, so we have to go back to the first row over here and replace all of these x primes and x double primes with values. So what do I have at the end?
Question. Why
Yes.
is it minus x? I thought that thing was...
There was a plus x here, so when you move everything, you move all of these terms to the other side.
Oh, you didn't...
I didn't convert, yeah.
Oh.
So now I have x1 prime is equal to x2, x2 prime is equal to x3, x3 prime is equal to x4, and x4 prime is equal to cosine 3t minus 6 times, and then x2, x double prime, x double prime is x3. x3 plus 3x prime is x2, and then minus x1 is the same as x. And there it is. So you see that the fourth order system produced the fourth order differential equation produced the fourth order system of linear equations. So the benefit over here, do you see any fourth derivatives here? No, right? There are no fourth derivatives. There's only a first derivative and then the functions over there. But guys, it's never a free lunch, right? You either deal with the higher order derivatives or you deal with a whole bunch of first order derivatives by multiple equations. And those equations are coupled. You see x2, x2 prime, x3, x3 prime. Right? That means coupled when these variables repeat throughout. Then you see that the last equation depends on x1 and x2 and x3. Right? And it plus has this cosine 3t floating about. So we are able to convert a system, we are able to convert a single equation, which is the third order or second order or fifth order, into a number of the first order linear equations. So that's a skill, and that later leads into a matrix and all of those things. The second type of conversion is when you have a system to put the system together into a higher order equation. And I see that one as far easier than this. But then again, you have your ways. So now the goal is to go the other way. Convert the system into a single higher order differential equation. Convert the system of DifEqs into a single higher order DifEq differential equation. What's fun? I want to know. Who's going to eat? So again, you have problems 11 through 20 that focus on that. I will do the first two, and then you deal with the other 8 for practice. So problem number 11. Again, you have book problems as well for this conversion. And after we're done with this, we'll just continue naturally into 5.2. My title has 5.1 and 5.2 in one shot, because we just continue what I do here. We're just going to continue and solve them. That's what it is. Lot to go. So the system is x prime equals y, and y prime equals negative x. That's the system. Now, this problem is symmetric and it's really kind of easy to deal with. So it doesn't matter if you differentiate first or the second equation because they're so simple. With the more draconian cases, if I should say, you guys will have to think which equation is better to work with. So right now what I'm going to do is I'm going to differentiate equation 2. And what I get is y double prime is equal to negative x prime. And now plug in. And you got y double prime is equal to negative, and instead of x prime, you just have y. So move that to this side, and there is your second order linear differential equation, constant coefficients. You know the solution for this, right? Because it's simple. You should know the solution for this just by looking at it. Of characteristic equation r squared plus 1, so it gives you sines and cosines, right? So
that's our solution?
well, we were just converting the system. We're not solving it.
Well, but that's the
Yeah, I hope you're not disappointed.
solution to this particular problem.
Yes. Would you like some peanuts?
I actually would. I was about to steal some
And then I moved it. Problem number 12. Oh, problem number 12, too easy. Let's find something more. Say for the test? Let's see something more, more substance. Yes. So it appears that problems 18, 19, and 20 would be the spiciest ones. So let's take 18. Yeah, 18, 19, 20 are what you would consider the next level. Right? X prime is negative y, and the y prime is 10x minus 7y. And in addition to this, we have initial condition x of 0 is equal to 2, and y of 0 is equal to negative 7. Yes. So both x and y are functions of t, so that x of 0 is x of t, so t is 0 and t is 0, x is 2 and y is negative 7. Now what I'm going to do is I'm going to convert this system into a single differential equation that it's only dependent on t. Cool? So, where do I start? Well, I differentiate this one and get y double prime is equal to 10x prime minus 7y prime. And then I plug in equation 1. So I have y double prime is equal to 10 times, and then instead of x prime I have negative y minus 7y prime. And then I put everything together into y double prime plus 7y prime plus 10y equals to 0. Now, clearly, y of 0 equals negative 7 is a cool initial condition to keep. But what I don't have is another initial condition over there. Yeah. So what should I do?
Have another piece of line. Page 3 right there.
Yeah, maybe there are some more civilians that would like to try it before I clean it. You're saving any of this, right? Are you saving any of it?
Can you make up the characteristic R1, R2?
No, I'm just asking what we do with this. We are not allowed to keep x. Oh, welcome. So we need another initial condition. And our equation on the bottom, clearly, is all in terms of y. So what do I do with that? Nice. You see this equation here? So you take these two guys, you plug them into that equation, and you come up with a solution. No coughing. So now for the, what do you call it? Initial condition, the second initial condition, we have that y prime is equal to 10x minus 7y, and that's the y prime of 0 is equal to 10 times x of 0 is 2, minus 7 times y of 0 is negative 7. So y prime of 0 is 20, minus and minus is a plus 49, we get 69. And there are our initial conditions. Y of 0 is negative 7, and y prime of 0 is 69. And we converted a system of two equations which were linear first order into a single equation here. Now you can go quickly solve this. You have the characteristic equation and you enjoy all of the stuff, right? So you see it's 5 and 2. So the answers are like e to the 2t, c1 e to the 2t plus, right? And you have the initial condition. Solve for these. So basically that's 5.1. There's also a theorem on uniqueness, existence and uniqueness for linear systems, which is, you know, always there, that the functions are continuous and the interval is continuous at the point A, then the given n numbers, the system is unique and the solution in an interval and satisfies the initial condition, which means that there is only one solution per system. Solution exists and it's unique. So if you change anything in the statement of the problem, that change will propagate through the problem and create a different answer. So there's a one-to-one correspondence between the answer and the... So that's 5.1. Now, continuing immediately into 5.2 is what we call the method of elimination. So now we get to eliminate. Well, what we just did in converting a system into a single equation is method of elimination, because we started with a system of linear equations which had x's and y's. X of t as one function, and then y of t as a different function. And we combined those into a single second order that was dependent only on y. So essentially we eliminated x, right? Eliminated x function. And I can solve that one first and then go back and figure the other one out. So let's take a look at this elimination system. What I can do is I could just continue working on this problem, or I can just take a fresh problem and go from there in a race to get to circuits as soon as possible, right? So method of elimination. It's problem number 2. You have some of the problems solved in your textbook. There we go. Is the stream alive? It's Barely moving, but it's moving. Okay, fine. So for this problem, we are going to use our standard stuff. You can differentiate this one to get y double prime is equal to 2x prime minus 3y prime. And what now? Yeah. Yes. So this method doesn't work this way, because now I have this to plug in here, but we are stuck there. If I plug all of this in there, my entire problem is again in terms of x's and y's, so it doesn't work this way. So we have to solve for x. Solve for x. X is equal to x prime plus 2y. Right, so shift 2y to the other side. And then you differentiate that one to get that x prime is equal to x double prime plus 2y prime. And now you have the equation over here. No, we're good, because we can solve for y from the first equation. It's really convoluted, but you have to do it. So now you have the y prime, so plug in, and you get x prime is equal to x double prime plus now 2 times 2x minus 3y. So far we have x prime is equal to x double prime plus 4x minus 6y. We can't have this y, but that's okay. I can solve from the top equation, right? From this equation, I can solve for y. So use first equation, which was x prime is equal to x minus 2y. So solve it. If you solve this for 2y, 2y is equal to x minus x prime. And then plug in. Now there is a neat trick over here. Instead of, right, you can understand this 6 as 2 times 3. So 2y times 3, so 3x, yep, plus 4x minus 3 times x minus x prime. X prime is equal to x double prime plus 4x minus 3x plus 3x prime. And now put everything on a pile and then shift everything to the left. So we x double prime plus x plus, who picked this? 3x prime, and now move everything on one side. So keep x double prime positive, plus 2x prime plus x equal to 0. Got it. Yes.
There's other ways to do this, right? Like you can use a.
Yeah, there's the rest of the chapter.
Yeah.
Very good. Yes?
What's the goal?
To solve the system. To get x of t equals to blah in terms of t's only, and y of t equals to blah in terms of t only. So we have two functions that are coupled, x of t and y of t, and we need to find them. So you know this system, if this over here were numbers, I don't know, 11 and 5, you know how to solve the system using elimination from basic algebra. Since this is a system of differential equations, these x's and y's are functions in terms of t, our solutions are going to be those functions in terms of t. So the goal is to find those functions. Yes?
Like, when would you want to use this method of elimination compared to the other?
Well, method of elimination is the one that transforms this into the linear equation that we can, of second order, right, that we can solve. So now if you look at this, I can make the characteristic equation. So, I mean, we are solving, so we have to now. So 2r plus 1 equals to 0.
I get that. Would there be a way where, hey, you can't use this method, you have to use something else? Like, well,
no.
you use this every time.
But we use the matrix as well to solve the same thing.
Okay, that's the way I learned it.
Then use the matrix. So this is r plus 1 squared equals to 0. So r is equal to negative 1 multiplicity 2. So we have a repeated root. And what happens when we have a repeated root? What happened? Not add. I need to multiply by x, yes. Yeah.
What, you add the x and...
Yeah. So we have that x of t. See, this is your question. What's the goal? The goal is to get this c1 e to the negative t plus c2 t e to the negative t. So that was your goal. But we are not nearly done. Easy with the attitude. We have to figure out why. Oh, did I mention that now these problems are like 15 pages? We need to find y of t.
All right.
Yeah. So now, how do I find y of t if I know x of t? There are a number of ways.
You just put it back in.
Yes. Now, the issue is that you don't have a simple equation that connects x and some constant multiples with y. They are connected to derivatives and all other terrible things. So, the hell is the equal sign? So now, if I want to solve for y, I need to use the equation that we had, 2y equals x minus x prime. So use 2y equals x minus x prime to get y solution.
So you just put it into
Yeah. So now this is going to be painful because we have to come up with a derivative of t first, x of t, right? Because that goes in the equation as well. So x prime is negative c1 e to the negative t plus the product rule over there.
Yeah.
So copy the first times the derivative of the second plus copy the second and the derivative of the first. There we go. And now we get to plug for, so y is equal to 1/2, and now we have x, which is c1 e to the negative t plus c2 t e negative t, minus the entire x prime thing, so that's going to be plus c1 e to the negative t, minus and minus gives again plus c2 t e negative t, and then a minus c2 e negative t. Yes? Yes?
solve this?
Y of t, well, we're not done yet because we have to simplify now. So we have the terms that have te negative t and te negative t. And we have the terms that do not have te negative t, right? So we start with 1/2. And I will combine these terms because these terms have only e to the negative t. Now, when you look at their coefficients, it's 2c1 minus c2. So 2c1 minus c2 as a coefficient of e to the negative t. And then, wait, these two terms are the same.
Yeah.
So plus 2 C2 e negative t. Nice. There's a t, yeah. So finally, y of t is equal to, when you distribute 1/2, you get 2c1 minus c2 over 2 e to the negative t plus c2 t e negative t. So what's the solution or answer? The answer is when you put everything together, so x of t was given as c1 e to the negative t plus c2 t e to negative t, and y of t is equal to 2c1 minus c2 over 2e negative t plus c2 t e negative t. There we go. Got it. And that's the solution. That's what we were after. Now you get initial conditions, you go calculate C1, C2. I mean, we don't have them in this problem, so this is where we end. But if those are provided, you have additional steps to solve. Yes. Oh yes, it gets worse.
Do you use this like with the vibrations and stuff like that, or anything?
Yeah, this is all, yeah. As I said, you have a spring and some kind of mass attached to it, and then another spring attached to that mass, and another mass on the bottom, and then you just like hit all of them and they start going, right?
Yeah.
The motion of those, right, is going to be modeled by two separate differential equations. When you focus on mass 1, you focus on mass 2. Each one of them has its own vibration pattern, and then each one of those gets its own differential equation. Now, clearly, the first object depends on the second object vibrations. So there is a link there to have these x's and y's on the same side. And then the bottom object obviously gets all of its motion from the dingling of the first one. So they're coupled, right? And they create this motion together. Electrical circuits, again, you have, in electrical circuit, you have a branch that connects the first loop with the second loop. It's the same branch that it's used in both.
Yeah.
It is going to have inductor or a capacitor or a resistor or something. And that's the link between the two, right? You have the current in one and current in the other. You have the voltage drops. So you write the Kirchhoff's laws going around the loop.
Right.
And some of the currents in the node to be zero, of all the currents coming in and all the currents coming out. You can do the whole thing in terms of the charge. So there are ways in which you can, connect all of these things. Now, the interesting part is when you get to circuits, right, you're solving the problems like this all the time. I'm not sure exactly what is the depth at which you go now. When I took circuits classes, Dr. Ahmed was going through this calculation, so we were getting solutions like this in terms of I1 is equal to, and then you have the whole spiel in terms of e to the t's and so on. And those who did not have differential equations, I mean, that was the end. In 3/4 of the course, electrical engineering, right? Because you do first direct currents, right? And then you hit with the alternating. This is how alternating circuits look like.
So that would be, yeah, if you're using those things.
Yeah.
But we end up, I think, doing towards the end when we're doing alternating currents, using that.
Yeah, but I can't imagine people going through and actually having honest problems in circuits.
We only did it like maybe once or twice or something like that. We didn't have honest problems like it.
Yeah, well, that's a problem
Because
because you
there's
don't.
different ways. The method, like what we used, was matrices to figure out most of our problems.
Yeah, well, we'll see that more of that in this chapter. So there we go. 15 pages ago, we had the system of two equations, and then we struggled, and eventually we got it into a single equation. And then once we get the single equation, after that it gets worse. Usually people say after you get the first one, then it gets easier, but no. Over here it gets worse. It computationally gets worse. I mean, you have your first equation. Problems 1 through 20. They give you 20 problems to enjoy. Sheesh. Exactly. 500 page later, you have glimpses of solution. There will be, these problems are more relevant to you when you see, I mean for circuits, when you see sines and cosines as driving terms, because you have alternating source. If you have a 60 hertz, 110 alternating current, right? You have your amplitude, and then you have the 60 hertz, and it's a cosine function, right, that drives the current. So your source, if it's alternating, it's going to be maybe 110 cosine of, and then you figure out the 60 hertz, what that works in terms of omega, and you plug that in. And it gets trickier for polyphase currents. This is only one phase against the neutral. So there are a lot of things that you have to consider. I mean, if you're going for electrical engineering, mathematics from here, you know, really skyrocket. Yes?
I was doing a problem based off vibrations, but if you use unit vectors, I was wondering if you used the unit vector to figure out amplitude. I didn't understand the whole idea why.
Unit vector by definition means vector of length 1.
Right.
So that has nothing to do with the amplitude. Amplitude is the coefficient, the constant multiple into the whole sine and cosine.
Why would it want to figure out what the amplitude is then?
Well, amplitude, when you say there is 110 volts in the outlet, well, it should be 118. So that means the amplitude of the wave coming in, of the source. And how quickly it changes positive, negative, positive, negative, positive, negative, it depends on the hertz, which is the frequency of the system.
But does it have, what's that have to do with unit vector there? Because it didn't make any sense why they went to unit vector. I was thinking it was the only thing to do with the amplitude because it was the amplitude position.
Nope. 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 We have time for another one of these examples, so let's enjoy one more with a smile. That's 5 people smiling. Exactly 6 are crying. And 2, please poke and see if they're alive. I'm just kidding. The people on the stream, what the hell is going on? You should be here. And you're not. So, where is my trig? Number 9 has trig on a first derivative. Number 14 has a trig on a second derivative. I mean, everyone wants to go home, so let's not do the second derivative. So coupled equations on the second derivative should produce the 4th degree equation. I hope that would be clear, right? So let's go with number 9. It has sines and cosines in it, so I like it. X prime is equal to 2x minus 3y plus 2 sine 2t, and y prime is equal to x minus 2y minus cosine 2t. Well, no initial conditions. I hope you're not disappointed. So we're not going to sleep here tonight. We're just going to try to put this together. What do we have? We have 45 minutes. Yeah, we're good. No, it's not going to be that. All right. So we solve for x in a second equation. Actually, how about you start this? Try to work a little bit on your own to get something somewhere, you know. So solve for x in a second equation. Differentiate, plug in, solve, flip, plug more in, and then hopefully you're there. Exactly. No, I have to go get my phone.
They're already in single terms. So
you can get all y's. Would you solve for x?
Yeah, solve for x. And then put that back in the y. So you make one where you send x equals x, right? And then you derive it, and then you put it back in the y. Something like that?
You got it, man. And then when you set it equal to each other.
Yeah. Minus rho is sine, which is a positive. But it's
using this one?
Well, you have to make it equal.
So x bar equal y prime plus 2y minus cosine 2t.
Yeah, plus y minus. Then you differentiate from there, right? Once you solve for x on the bottom here. Or it all depends on what term you use, right?
Differential equations are funny.
Yeah, but it's interchangeable, so it's minus 2.
As I said, 5 people are smiling, 6 are crying, and we are not sure if those 2 are alive.
Professor, why this one? It's like a free integration by parts integration.
Beautiful.
No. Well, hard. This is Thanksgiving. I'm not thankful.
You are welcome.
Integral.
Celebrating at that point.
Chain rule. Copy the first. One of the cosine.
Yeah.
How do you say it on George?
75 pounds of sugar in this one. Nice. You practically bought a bag. Okay.
Like I know there's confectioner's sugar in the frosting, but like I didn't actually have to get a cup of sugar. Just everything already has sugar.
You would have added a little bit for a good measure.
Yeah.
Because I don't think that everyone who tries it would die from this amount. But if you add a little bit more, definitely everyone. Nice. Very good.
Can you?
Yeah.
You look like you're a really good player.
I look like that? Oh yeah, because I'm fat? Yeah.
No, you're
Wait, so am I doing the opposite? I'm getting Y's instead of...
I don't really know how to do it.
The good thing is it's not on the next step, right?
Yeah, right.
Of course it is.
I know very.
On the test, do we get the choice between variation of parameters and the other one? Or?
If it doesn't say yes, but if it says no.
Okay, so we should definitely make sure we know both.
Both, yes.
Okay.
Well, one is the procedure, the other one is the formula. And the formula is not that bad to memorize, right?
Yeah.
All right.
You already had the next one.
So we're plugging out into your Wi-Fi. So everything for
Please.
You made it?
No. Lauren, man.
No, she did.
Lauren. I said Lauren, and you turned to Ryan and said,
I heard Ryan, I'm like, wait, you made it?
I can do math. I can't create masterpieces like that.
I was gonna say, you don't look like the cooking type.
Yeah, but
This is
math is
not.
art. That's what it is. I got an idea for that.
Oh wait, are these like
I'll
peanut
give you the
butter?
carpet
She
as
could
well.
actually do math too, so she's just everything.
Yeah, most of the time you're waiting for it.
Can you sort the problem?
That's what I'm having difficulty with because I'm.
All right, let's
prime in there and I don't know what to do with it.
let's take a look at this problem together. And then when we get stuck, we'll ask Kevin.
First step, solve for x.
Yeah. Oh, by the way, first, congratulations to Evan, everyone, because he received the President's Volunteer Service Award on Saturday.
Who is this?
Evan, right there.
150 hours?
Yep.
100. I'm not home.
So he volunteered this past year a lot, and we submitted the award. It was we nominated him, and the award came in. So on Saturday he received the award. It's a pin and a certificate and a letter from the United States President. That's it.
I got a letter from the president.
It's not even a letter for
Actually,
It is.
I got a total.
It is a letter.
There's 3 letters.
Yeah, first person.
It's got the signature at the end.
Uh-huh.
Do you really think that Donald?
All right. Ready?
Evan, save some awesomeness for the rest of us.
Solve for x or no?
Yes. So x is equal to y prime plus 2y plus cosine 2t. And now we are going to differentiate that, get x prime is equal to y prime plus no, y double prime plus 2y
Prime. Minus.
minus 2 sine 2t.
Yeah.
Bueno? Now we know what x prime is, and we are going to replace that in.
With the y prime goes in where the 2y prime is, right?
Now you can replace x prime by
Yeah.
Well, could you also put that original y prime back in for that 2y prime? Like the x
In the
minus
middle
2y
term?
in the middle term?
See the plus 2y prime in the new equation? Can you do that? or-
Over here?
Yeah.
I mean,
2 times that whole equation, does it make it longer or is it indifferent?
I don't know, you try it. It's there are no rules.
What's the best way? How about that?
I don't know.
Oh,
These are every problem
Testing us.
every problem is different. Yeah. So you try, you see what works better, what works, right? It's there's no prescribed way. You are just shoveling equations until you get everything in terms of, in this case, everything in terms of y. So no x's anywhere. So you have choices now.
It actually might be better if you just put it into that x prime because then you only got the one x.
Yes, and then you solve for x from here. I mean, you plug this in again, and that's it. Yeah.
I don't know if I can write it. I'm kidding.
He's
I
got
got
the
pretty
angle.
far with it. I got pretty far with
So our backup plan of trying to figure out if I can do it right is
it. This is disgusting.
failure.
This is actually disgusting.
2x minus 3, get out. Y plus 2 sine t. Next row. So instead of x prime, I will put, so instead of x prime, I have this that goes in. So I have 2x minus 3y plus 2 sine 2t is equal to y double prime plus 2y prime minus 2 sine 2t. No, they add,
Oh yeah.
because they're opposite sign, right?
Oh.
So now, y double prime plus 2y prime minus 4 sine 2t, and then we have minus 2x and plus 3y equals to 0. So I put everything on a pile. Now I have the 2x that it's not supposed to be there. So I will plug in this equation. So now we'll go with the purple. So we know what plugs where. So y double prime plus 2y prime. This I'm going to ship to the other side.
Which one? The minus.
The minus 4, yeah, cosine. So minus 2 times, and I have over here y prime plus 2y, and then plus cosine 2t, and then plus 3y equals to 4 sine 2t.
And you only have to derive once.
Yep.
Wow, that makes it so much easier.
Yeah, I know. Try the second order. You'll see how beautiful this is. Right.
Is that a joke?
Do you want it to be a joke?
When do I joke?
He's never
This is differential equations.
This whole semester, everything he said is serious.
Plus 2y prime. Oh, plus 2y prime minus 2y prime, that dies. Right? And then you have plus y is equal to 4 sine 2t plus cosine 2t. Beautiful.
Hold on. It's negative 4y plus 3y, so it's negative y.
Yeah, it's clearly negative y. If you look at it, right, it's negative y. You can see it's a negative 4, and then plus 3 is negative 1. Yeah. Pay attention. And there it is. The system converted into this second order constant coefficients equation, and it's non-homogeneous.
I think this is probably the easiest part we don't want to discuss about.
Yeah.
Is it just me solving that? Like, I'm doing variation parameters, so I feel like I'm doing that wrong. Like,
Why would you do that?
Like, that seems. Okay. Don't do variation parameters.
You guys do it?
Yeah.
They did undetermined.
All right. So since the exam is coming up, would anyone teach me the undetermined coefficients? What am I supposed to do for undetermined coefficients?
They know.
Take the derivatives and plug in, right?
Yeah, that's simple.
All right. So we start with the homogeneous case first.
Yep.
Guys, technically what I'm doing right now is a review for your exam. Because this over here, this conversion, plugging stuff in, converting the system into a single equation, that's 5.1 and 5.2, which we learned now. After, when you just see this problem, I could just literally copy and paste this on your exam, because this is something that you are supposed to know how to solve for the exam. Now, if I write on the exam, use variational parameters, you use variational parameters. If I say undetermined, you use undetermined. If I don't say anything, use whatever you want. That's the way it goes. So now, y double prime minus y equal to 0 has the coefficients of -1 and +1, which gives us hyperbolic solutions. But we can, you can either express them as hyperbolic solutions, or you can express them as ease, whatever your heart desires. So you like ease, there you go. Y, homogeneous part, is going to be C1e to the t plus C2e to the -t. So that's the solution that you get. You will get the r squared minus 1. R squared minus 1 factors into r minus 1, r plus 1, giving r1 and r -1. And there you have the homogeneous part. Now, for the particular solution, you are supposed to take 5,000 derivatives of this, right? And you quickly see that every time you take derivative of sine, it oscillates between sine and cosine. And every time you take derivative of cosine, it oscillates between cosine and sine. The only thing that is changing all the time are these two numbers here, right? So +4 will in next step change into 8, and then the following step into -16, and so on. And then the +1 that you have over there, +1, will turn into a -2, and then +4, and so on. So that the derivatives for the particular solution, yp, give us the form of a sine 2t plus b cosine 2t. Yes. And now we take two derivatives of this one. So yp prime, which is for the first derivative, we have 2a cosine 2t minus 2b sine 2t. And then we take the second derivative so we can plug in our equation. So one more is -4a sine 2t, and then minus 4b cosine 2t. Now we plug this one over, I wanted the color, come on. This one over here, and this one over there, and then work it out. And equal it to whatever we have. So we have minus 4a sine 2t minus 4b cosine 2t minus a sine 2t minus b cosine 2t. Right, when you distribute the minus, is equal to 4 sine 2t plus cosine 2t.
And all the
Put all the signs together, so you have minus 4a minus, oh, that actually is just a negative 5a, right? This puppy and this puppy, it's negative. So negative 5a sine 2t,
and then negative 5.
negative 5b cosine 2t is equal to 4 sine 2t plus, is this good?
Yeah, that's good.
No, because they're laughing, so I was,
Yeah, it's good. Wait, no. You forgot the 2 cosine. You have cosine.
what happened? 2 cosine 2, what happened?
You have 2 cosine.
Where?
In front. 2, I don't know. You lost the 2 somewhere.
Yeah, but why?
Where did I lose my 2?
Because it's minus 2 times y prime.
Oh, there is a 2 over here.
Wow, that messed everything up. Okay, read here.
There's a 2. So that makes 2 over here
Point.
and makes a 2 over here. All right. Negative 5b, well, thank you. I need more sugar now. So a is equal to negative 4/5 and b is equal to negative 2/5. Oh, we are at a half. We're good. It's a half of the problem, almost done. So, because this only gives us y, and then we have to figure out x,
Yeah.
right? Yeah. So, what we have is that y of t is equal to c1 e to the t plus c2 e to the negative t, and then we have to add yp, right? And the yp is this one with a and b, so we have those numbers. So that's negative 4/5 sine 2t minus 2/5 cosine 2t. All right, so we got y. Now we are supposed to find x. So now we find x of t using the formula that connected these guys, and that formula was right there, the purple one, y prime plus 2y. So y prime plus 2y. Oh wait, the x equals, right?
Yeah.
X equals y prime plus 2y plus cosine 2t. That was it, right? Nothing else. Just that. Yep, good. Well, in order for us to use this formula, we have y to plug in. We need y prime. So now I need to differentiate this and get my y prime, which is c1 e to the t minus c2 e to the minus t. And then derivative over here is minus 8/5 cosine 2t. And then the derivative of cosine is negative sine, so plus 4/5 of sine 2t. That's the derivative.
Now we gotta put all that in there.
So now, yes.
And round on the paper.
Well, oh, I didn't mention that you should keep your notebooks landscape.
Yeah.
Oh.
No, I learned that in the homework.
So now, what's x of t? X of t is equal to, we have y prime, which is c1 e to the t minus c2 e to the negative t minus 8/5 cosine 2t plus 4/5 sine 2t, plus 2 times the y of t, which is c1 e to the t plus c2 2e to the negative t minus 4/5 sine 2t minus 2/5 cosine 2t. And finally, we have just plus cosine 2t. Like, it's there at the end.
It's like that movie in Spaceballs when the ship just doesn't stop going by.
Yeah.
Yeah. Never.
So x of t is, and now we put all of the e to the t together, so all of the coefficients of e to the t. So we have a c1 plus 2c1 is 3c1. So 3c1 e to the t, and then e to the negative t is plus c2 e to the negative t. So this and this.
Yeah, once.
Now, yeah, so now add the signs together. So, yeah, but you have a one extra because there are two in front. So one survives. So negative 4/5 sine 2t. And for the cosine,
That's 4/5 and negative 8/5. So that's going to be negative 4/5.
yeah, negative 4/5, so that's negative 12/5. And you have negative 12/5, and then you have plus 1, so negative 7/5 cosine 2t. If you're not paying attention, then you might get lost in where the 7/5 came from. So I have 3 cosines. I have 2 sines to combine, but I have 3 cosines to combine. So for sines, I have 1 of 4/5 and 2 of negative 4/5. So 1 of the 4/5 will cancel the 1 of the 2 of negative 4/5. So that means that 1 of the negative 4/5 survives, which is the one that I have here.
Okay.
So sines are easy. But the cosines are evil because I have a cosine here, and I have a cosine here, and I also have a cosine there. So minus 8 minus 8 minus 4/5 is minus 12/5, and then I have 5/5 here, which gives us negative 7/5. And we finally have x of t, and then couple that with y of t, which is equal to whatever it was, c1 e to the t plus c2 e to the negative t, and then we have the sines and cosines, minus 4/5 sine 2t. This looks like a 6, it should be a 4. And then something else, minus 2/5 cosine 2t. And then these two together gave you, this was what we were after. So
like one of those problems is going to be like, for like 5 problems over this.
Oh my god.
yeah, now you know why differential equations is easy to have 3 problems, right? It's no problem.
Yeah. What's it hard?
You have to draw the line between hard and annoying. There is nothing hard over
This
here.
is not hard. This is annoying.
There is nothing hard over here. This is just
It's just the right.
a lot of calculations on top of each other, a lot of concepts pulled together, but this is the work that you really don't want to do because it's not thought challenging, it's just a grind, endless grind. So yeah, it's labeled as annoying rather than hard.
I mean, it's difficult in the sense that there's a lot of opportunities to mess up.
Right.
Again,
Coffee.
I mean, would you say that it's difficult to drive?
Yes.
And then look up at the and the wonderful.
Well, driving's not bad. Why do you do it? My driving's bad.
It's difficult.
Driving in my brother's car is bad.
Why?
He's got one of those. He's got one of those soccer mom minivans.
Like Tesla Model X? All right. So I hope you enjoyed this experience. We solved 2 examples for each one of these. This lecture continues. You guys want to leave? This was the first half. And now we defined the linear differential operators. So what we just did is what example 1 described in 5.2. Now we're moving on the second part of the lecture. We have 7 minutes, so yeah. And in the second part of the lecture, we learn about a linear differential operator, which is what you apply to a function to differentiate. So it's a little bit tricky to understand this, so I'll try a different approach than what the book gives. Obviously, you already read the book, so you know what they say. The notation that you have, that the derivative of x squared is 2x, I am going to change that notation into a new notation which will say d of x squared, and you still have your 2x. And then if I want to give the second derivative of x squared, which we know is 2, I will put d squared of x squared, and I will get the 2. So we are shifting the notation from your standard d dx and then d squared over dx squared and so on. We are shifting that notation into this capital D notation. And there is also equivalent for Calc 3 with a capital D with a little x and a capital D with a little y, which denotes partial derivatives. Now, this notation is preferred in linear algebra to use the right? You take
we just did that.
You just did that? Oh, so you can teach instead of me over here while I
need a refresher course.
You forgot that class. The whole class is a blur.
Yep. So you forget matrices? No, I get those.
Great.
Transformations, all that, yeah. And the reason why is because I haven't used it for anything in real life. In the real world.
Well, I mean, you could use it for real things.
All right. So let's talk about these things. So now, imagine. So this is going to be a simplified intro, and then you guys will drill deeper. We'll take a look again at this after the break. But let's just take a look at the standard x double prime plus 3x prime minus 4x equals to 0. So I know that x is a function of t, right? That's what we have. So x is not a variable, x is a function. Now, the first term is written as the second derivative in respect to t of x plus 3 times the first derivative in respect to t of x and minus 0th derivative, and that's equal to 0. So now this would be given as d squared of x plus 3d of x minus 4x equals to 0. So just converting the notation from what you're used to so far into this new model where you are representing everything in terms of this x. And now, what I'm going to do is I'm going to factor x out. So what that leaves behind, it leaves the differential polynomial operator. So it leaves the d squared plus 3d minus 4, all of that applied to this x equal to 0. So this puppy over here is known as a polynomial differential operator. So I can give you just the operator, and from that operator you should be able to retrieve differential equation. So I can work with differential operators rather than working with the entire differential equation. Now this stuff is extremely powerful because it's going to turn your linear systems of differential equations into a systems of basic equations. And then you solve those. Remember how Laplace transformed the problem into a basic equation and then you had to use inverse Laplace? Well, you're going to have something similar here. We're going to sneak in some matrices and do some cute stuff. If you figure out right time over the break, look into matrices. And on Saturday, what time we were meeting? 8 a.m. So we are going to go back and work on chapter 2, work on chapter 3, work on chapter 4 to reinforce those.
Like we'll see on the test.
And yeah, we'll see those kind of things. So I'll see you all on Saturday, 8 a.m. Yes, this classroom. So